Okay, so welcome back. Let's wait for 5 more minutes to see if other people join. Then we can start. Okay, so I think we are good to go. So, yeah. So, welcome everyone. This is NOC24 W139 NPTEL tutorial session on Microelectronics devices to circuits. The instructor is Professor Surya Das Gupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So, this is week 6. So, these are the prerequisites which you already must be familiar with. So one announcement is that next week's session will not be on Sunday, but next week's session will be held on Friday 6 to 8 p.m. Okay. You will get the announcement by the NPTEL team. So yeah, let's begin. So do anyone of the attendees like to answer this question? CMOS inverter can be used as an amplifier when? So if you draw the V out versus V in of an inverter. First, let me do what an inverter actually is. Linear region, I do not think so. Let's explore them in detail. So, this is basically what an inverter is, right? This is your V out, this is your V in. So, this is a P MOSFET and this is an N MOSFET. Okay. So the connection is something like this. So if you plot the VTC, it will be something like this. So let's say these are the VDDs. So in this region, you can see that the slope is quite high. So it can be used as an amplifier in this region. Now the question is, how do we get this voltage transfer characteristics and what are the uh, main fundamentals behind this, right? So let's start with, let me add one page. Okay. So let's start with this. So from this diagram, can anyone of you tell me that what are the terminals? So obviously these are gate terminals, right? So this is source of an NMOS. This is the drain of an NMOS. This is the drain of PMOS. And this is the source of PMOS. So is this part okay with you?
Yes, sir.
Okay. So now we mark two things, right? Let's say we discuss about PMOS. So what is my, so when will my PMOS be on, means how to check that? So let's say here we check our source to gate voltage, right? What is the source to gate voltage in this case? VSG, let's say VSGP. What is that? Source to gate voltage of the PMOS from this diagram. So it is simply Vs minus Vg, right? So what is that for PMOS from the diagram?
So VDD.
So VDD is your source voltage, right?
Yes,
And
sir.
what is the gate voltage of the PMOS?
VN.
So what will be this? VSG,
VDD minus VN.
right? So it is your VDD minus Vin. And what about the source to drain voltage?
VDD minus V out.
So VSTP is your VDD minus V out. Now let's look at the NMOS. What is the gate to source voltage? Because I need these two voltages to get the current equation or trend, right? If you see your
Yes.
MOSFET current equations, you need to know your gate to source voltage and also drain to source voltage. But in case of PMOS, we just the polarity will be opposite because your source will be always at the higher potential. So gate to source voltage VGSN is equal to your V in
V.
and your drain to source voltage is your VDSN
Out.
is your V out. Right? So now what we will do, we will try to plot this from this information and whatever the basic MOSFET physics we understand or the equations we know. So let's say the current flowing through this transistor is I, let's say I out. So this same current will be flowing through the entire stuff, right? Because this is connected in series, there is no other path for the current to go. V out, I am just probing, right? That means that is an open circuit point where I connect my voltmeter and measure V out. Do you understand?
Yes. Yes, sir.
So the entire I0 should be flowing through both the transistors. Now I need to see with my V out how my I0 will be behaving. So what I'll do, I'll plot here V out and I'll plot here your I naught. Okay. So
Yes.
for the case of, okay, just let me change the color of the axis. So for the case of NMOS, let's say my V in is 0. So what will be the current IDVD of, so this is simply IDVD, right? For my NMOS. For my NMOS, this is ID and this is VDS, right? So if
Yes.
my VG is 0 or my V in is 0, this quantity is 0. So I should get a current, 0 current at this point,
Yes.
and this trend will follow for my V in less than equal to VTN or the threshold voltage of the NMOS, because below threshold voltage of the NMOS, my MOSFET is off. So current flow will be 0. Fine.
Yes, sir.
Now, what is the case of NMOS? What is the case for PMOS? What is the case for PMOS? For PMOS, when my V in is 0, so what is my VSG?
Sir, VDD.
VDD. So that means PMOS is turned on.
Hmm.
So PMOS will have a characteristic something like this. Let's say, let's mark a point here. That is my VDD. So PMOS will have a characteristic something like this, right? This
Yes,
is
sir.
this is the case for V in equal to 0. Now, what about V in equal to VTN? What will be then VSG of the PMOS if V in equal to VTN? It will be
Sir,
VDD
V.
minus VTN, right? That
Yes,
value
sir.
will be dropped. So that means I
Hmm.
will get a curve something like this. Do you see? This is the case
Yes, sir.
when my V in is equal to VTN. So what is the output voltage? That will be determined by when my two current curves intersects, right? So let's say in this region, my output point will be fixed at this. Fine. Whatever current my PMOS can have, but my NMOS will be having, simply speaking, in this case, whatever so far we have discussed, what will happen? my PMOS will be, let's say I just draw the symbol as I have shown. So my PMOS will be turned on, but my NMOS will be open always, right? Because no current is flowing. So whatever my VDD is present, that will be simply come to my Vout. So my Vout will always remain to VDD when my Vin is 0 to threshold voltage of the NMOS. Okay.
Yes, sir.
So this translates to, let's say I draw another plot just beneath this. Let's say this is my V in and this is my V out. So far what I have done, I have plotted
PMOS
till this much,
till Vn is equal to Vth.
0 to VTN. Until that point, my output voltage will be remaining at VDD. Right? So
Yes.
far we have got this. Now let's see the other extreme. That means I am just now tuning down my V in from VDD to some lower value. So when my V in is equal to VDD, let's concentrate on this case. What will happen? This PMOS will be on. This NMOS will be on, right? So your
Yes.
NMOS characteristics will be something like this, let's say. But what about the PMOS? In case of
PMOS will
PMOS,
be off.
then your PMOS input voltage is VDD minus VDD, that is 0, right? So it is not
Yes.
beyond your threshold. So it will be simply following this line, right?
Yes.
And till how far it will remain in this red line? This will remain until my V in is
Is less than
dropped from
Vth.
VDD minus VTP, the threshold voltage of the PMOS. As soon as my V in is less than VTP, so VSGP is VDD minus VTP, right? So this cancel, this becomes VTP. Okay. So as soon as it is less than this value, my PMOS starts to conduct. But till then, PMOS output characteristics will be fixed at this value. But however, my NMOS will start to
Decrease.
decrease. Why? Because now my Vin is not, VGS is not VDD. It is my VDD minus some lower value, VTP. So considering that, what is the cross section point? It is at 0. So that means if I have a value here, this is VDD and let's say this value is VTP. So at this, between this range, my output is fixated at 0 value. Fine. Now comes the question, what is happening in between? Now let's say we start to increase our Vi beyond VTN. What will happen? Then my NMOS will not remain at this black line. It will also start to conduct.
Yes, sir.
My NMOS will also start to conduct. And my PMOS will keep falling.
Yes.
Similarly, from the other side, if you see, in this case, my PMOS will start to conduct and NMOS value will start to keep falling. Okay. So now what is the intersections? In this case, my intersection was this, right? And in this case, my intersection is this. Similarly, there will be a point when both of my current levels will be at the similar range, or it is something like this. So you see how the green point or the crossover point of two currents, because my V out is determined by the balancing of two currents, PMOS current and NMOS current, and those two currents has to be same. That is why we are taking the cross section point of the two currents, because at that point only my two currents are same and two currents are in series. So that's why we are taking the cross section point or the green points. So if you see now, your this, as you start increasing, your this point will start to drop and it will fall something like this. So it will follow some characteristics like this. So this is how you got your voltage transfer characteristics of your inverter. Now let me mark two more regions. So let's say this is one region. In this region, what is the status of my PMOS and NMOS? In this region, let's say, let me highlight it. In this region, what is the status of my PMOS and NMOS?
NMOS is in cutoff and PMOS is in linear region.
This is the case when my output is at this. So NMOS is in, so let's say NMOS is off and PMOS is in linear region. And what about this region?
So it will be opposite. PMOS will be
PMOS
off,
will be off and your NMOS will be
linear region.
linear region. So can you tell me that what about these regions? This point, let's say we take this one point. Let's say we take this point. So output is in this region, right? So what is the status here? PMOS and NMOS.
So NMOS will be on.
On means what region? On can be in linear and saturation both, right? Look at this green point. This green point. Because this is my near to VDD, right?
Yes, sir.
This is my near to VDD. So at this point, what is the status of my PMOS and what is the status of my NMOS? So you can see, right? This is the intersection of
Yes.
which two curves? This is the intersection of this curve and let's say this curve.
Yes, sir.
So black curve is for NMOS. So which region is this point of NMOS?
So saturation.
So NMOS is in saturation, okay? And what about PMOS?
PMOS is in linear
Look at
only.
this yellow highlighted red curve
It is
and the
linear only.
linear region, right?
Hmm.
Now similarly, if you look at this curve, this green highlighted curve and this red highlighted curve. So this is the point near to your zero, right? So that means this point will lie somewhere around here, let's say this point. So what is the status of PMOS and NMOS then?
Sir, here NMOS is in saturation And
Look
no,
very
sir.
carefully.
PMOS is in saturation and NMOS is in linear.
PMOS is in saturation, NMOS is in linear, right?
Yes.
And what about this region, this intermediate region? This region is your, this blue highlighted region is this point.
Yeah. So both are in saturation.
So your both PMOS and NMOS are in saturation region, right?
Yes, sir.
So that means what? The high gain region, your both MOSFETs has to be in saturation region. Why it is a high
Yes, sir.
gain region? What is your gain? Your gain is, the voltage gain is nothing but dV out over dV in, right? The slope of the input
Yes.
output characteristics. So if you just
Yes.
plot the slope, so how will it look like? So this is your AV and this is your V in. So let's say this is your VTN and let's say this is your VTP. So beyond this it is 0. Beyond this it is 0. This is 0, right? The slope of this line is 0.
Yes, sir.
The slope of this line is also 0. And beyond that it starts to drop and then increase and get back to 0. So what is this region?
Saturation.
So this is the your high gain region, right? So between these points you can use the device as an amplifier. Why? Because your gain is very high. Maybe it is an inverting amplifier, you have a minus sign because of the negative gain, but your magnitude of the gain is there, right? So if you have a, let's say, what does that mean? That means that if you have an inverter, if you put a very small signal, you get an inverted large signal. Fine.
Yes, sir.
So this is how your inverter can be used as an amplifier. But do you see the main crux of how this region has come about? Means why? First of all, the question is, let me just phrase the question, that what dictates. So first thing is that both PMOS and NMOS is in saturation region is the right option. Then what dictates the value of gain? Means how, let's say this is my AV max. So how high will be AV max? What can dictate that? From this analysis, can you tell me what is the key behind this high gain? One thing is for sure that, let's say this is your V out, this is your V in, and I give you two curves. One is this, another one is this. So which one has higher gain?
So red.
Red one has higher gain. So how can we get the red curve from the IV characteristics? What determines that?
So the slope is high of red curve.
What slope?
The slope of red curve is greater.
Slope of red curve is greater, right? So that means that will
Yes.
give me a good amplifier.
Yes, sir.
But good amplifier in the sense high gain, not good amplifier, high gain.
Yeah.
So my question is, what characteristics of the of from this curve determines that high slope? So maybe it is not so easy to see for you. Let's say this is your I naught, this is your V out. So let me give you two scenarios. The red one is a curve something like this, and the black one is a curve something like this. Okay.
Yes, sir.
So what is the difference? This is a long channel device and this is a short channel device. So there will be channel length modulation, there will be drain induced barrier lowering, etc. Okay,
Yes, sir.
which makes your R out not equals to infinity. But in this case, your R out is equal to infinity.
Yes, sir.
Okay. So now coming back to the discussion, let's say your PMOS curve is something like this for multiple values. So do you see the fact that the flatness of IDVD of PMOS and NMOS in their saturation region gives you the gain region of VTC? What happens when two almost parallel lines intersect with each other? So let me show you it more clearly. So let's say this is one line, okay? And this is another flat line. So you have the intersection point at this
Yes,
position.
sir.
Now you are
Yes.
increasing your V in. So what will happen? This will increase. V in
Yes.
increasing means what? Your IDVT's magnitude is increasing. Gate voltage is increasing means what? You are increasing it like this. I am just drawing this portion, okay?
Yes, sir.
And what about your this curve? This will decrease then. If NMOS increases, NMOS, if your input, we have seen, right? If your input voltage increases, so your one IDVT curve increases, another IDVT curve decreases the magnitude for obvious reasons because this is in opposite sign. So now you observe that the next point has intersection at this point. So this is the value of your delta V out. You just understand that these plots are something like this. Okay, it has something like this. Then your these are nothing but your IDVD plots. Okay, I
Yes,
am
sir.
just drawing the flat portion to make you understand that why this where from where this gain is coming. And what is your input difference here? Input difference is this much, right? This is V in square. Why V in square? Because your this is ID scale. ID is proportional to VGS minus VTH whole square, right? In saturation region.
Yes, sir.
So this small change of V in is causing a large change of V out. And this is happening because both transistor are in saturation and this region is flatter. That means two flat lines are crossing each other. So a simple shift vertically will change this point from this red point to green point, a large amount of shift. Okay. So this is what is happening when you are applying a small signal swing at the input and you are getting a large signal swing at the output. Okay.
Yes, sir. Got it.
So this is the fundamental behind it. So if you remember, if you have understood this and can remember this part, you will never forget that your PMOS and NMOS both are in saturation in the high gain region of the VTC. Why? Because that high gain region comes from the flat
That's
portion,
the
and
flat
flat portion are the saturation regions. Okay.
saturation. Yes, I got it.
Okay. So this is how you plot your VTC. Fine. Do I need to discuss anything more on this? Okay. So no. I think you got the idea. So moving on to the next question. Okay. So find the optimal size of the inverter in the following inverter chain. Okay. Consider an input capacitance this, load capacitance this, and this. Okay. So how do you optimize your inverter? Means what are the considerations you should have? So you should consider delay, power dissipation, right?
Yes.
So we'll first discuss how to optimize the inverter from the delay point of view. So delay in inverters. By the way, yeah, just let me point this out one thing, that if you draw a line, this line is your V in equals to V out. So the point at which it crosses the VTC is called VM. So your VM is called your switching threshold. Okay. So what is switching threshold? Switching threshold means beyond it you can around this point you cannot tell whether you are at level 1 or level 0. So basically in digital designs, this region is your level 1, okay, and this region is your level 0, but around this point you cannot tell that what is your level 1 and level 0. By the way, in this regard, one question I just thought to ask you. So this is one in your VTC, another one is this is one VTC. So which is a better amplifier?
So the red one is the better.
From what point of view?
So because its switching threshold is very high, like it switches
Switching
in a
threshold, no,
very
not
short
switching
period of time.
threshold. Your gain is high, right?
Yes, gain is
Not
high.
switching threshold. Switching threshold in the both case will be around this. Around will be your VDD by 2. Switching threshold means what? Switching threshold means the point at which around which you cannot differentiate. Okay. So this will be around your, for a good inverter it will be around VDD by 2. But there is a formula you can derive based upon the your width ratio of the PMOS and NMOS. But from this, uh, just think for a minute that what do you think, that red one is better for an amplifier from the gain point of view, right? And what is from stability point of view? You see that only in this region you can get the gain, right?
Yes, sir.
As soon as you are deviating from this region, so your gain drops to zero. Your gain is dropping to zero, right?
Yes, sir.
So first thing is, to amplify you need to have to be in this region. Now suppose this is your bias point, you have biased, this is where you have biased, and you have a signal, input signal swing like this. So if your input signal is not small enough, right, a slight shift will take your output to these points in the red plot,
Yes, sir.
because you have a very narrow room, right? In case of red plot, the region of the input where you can operate is very narrow. But in case of black plot, the region becomes a very wide. So you can have a trade-off. You see the point?
Yes,
The
sir.
point is, in case of red curve, is you cannot amplify a sufficiently larger amount of analog signal. Means your
Hmm.
signal amplitude has to be very low. Otherwise, it will change the bias point and shift it to this region where you do not have any gain. For that matter, your signal will be simply lost.
Yes, sir. Got it.
So you cannot say directly that your red one will give you a better amplifier than the black one. It depends on your preference and the application. Okay.
Yes.
So don't make this mistake in the interviews. So yeah, coming back to that, we are talking about delays in the inverter. So when you think about delay in circuits, what is the first thing come into your mind?
So time lag is there.
Sorry?
So due to the delay, time lag is there in receiving the output.
Yes, obviously. Let's say what you answered is that, let's say you have a logic circuit, or for that matter any circuit. This is your input and this is your output. For the input to propagate through the circuit and output, it occurs certain delay. Okay. So this delay we sometimes call it propagation delay. We'll define these terms, but the point is, whenever, let's say if I give you a metal wire, okay, so if I give a signal, so how much time the signal you think takes from passing this point to that point? An ideal metal wire, if you give signal to one end, how much time it should take to reach the other point?
So an ideal what?
Ideal metal wire, metal line, let's say,
So it will reach without any time.
instantaneously, right?
Yes, sir.
So let's say now I give you a resistance. Then what will be the time?
So time will reduce due to the resistance.
Why?
So because resistance will oppose the input from going to the output.
Let's say I give you this input. Okay. So this is your V. Let's say this is the input. This is T equal to T1, T equal to T2. You are asked to calculate I. I will also, you will be just doing the same thing from Ohm's law,
Yes, sir.
right? So it will be instantaneous, right? Until unless you have some storing element which lacks the current with, or leads the current with respect to voltage. You see, you have read, right? In capacitances, currents and voltage has a phase shift of 90 degree.
Yes, sir.
So again, you need to have some RC elements in the circuit. Let me ask you another question. So this is a capacitor, okay? and now you have given a input signal like this. What will be the output characteristics?
like RAM signal.
Huh?
RAM signal,
Why do you say so?
because integration is there. Storing element,
Storing element. So at t equal to 0, what will be the slope? So this is your V in, okay? So what will be the V out? So you mean to say V out. So your I is what? I is your C dV out over dt, right?
Yes, sir.
So the capacitor will charge with a time constant equal to, how will the capacitor charge? Capacitor charges instantaneously, right? Because you have no lag. For the lag to be present, you need to have a resistive element that will delay your charging. If your resistance is 0, your RC is 0, tau is 0. That means instantaneously your capacitor will be charged.
Yes, sir.
So remember this point in the discussion when we'll discuss when the discussion goes forward. Okay. So now for the time being, we are defining some TP. So we have to understand what TP means actually. So let's say this is time axis and this is your input signal. So let's say this is the signal is something like this. So this value we let's say call it 1. Let's say VDD 1, same thing. And this is 0. And let's define a midpoint, that is your zero point 0.5. Okay, or the 50% level. And let's say at the output your circuit is an inverter. So what will happen? This will be starting at 1, then this will fall, then after some time it will go up again. So, and let's also mark the midpoints. This is 1, this is 0, this is 0.5, and this is your V out. So we have a delay associated with these 2 points. This we call it TPHL. Similarly, from this 50% point to this 50% point, we call it TP. TP stands for propagation delay, and HL and LH are stand for. So
I
your
to
TPHL is propagation delay for
I to
output high to low. Always remember that we always define propagation from output state change, means output is changing from high to low. So that is why we are defining this as TPHL and this one is TPLH, because in the blue curve it is just the opposite, right? So always remember that propagation delay is defined on the output. So, and overall propagation delay, your TP is defined as your TPHL plus your TPLH and the average of these two. One thing is, you can note that this TPHL may not be same as TPLH, okay? Value wise, magnitude. Even you can construct a circuit where TPHL or TPLH can be negative. That is possible, okay? However, the average will always be positive, because if one is negative, other one will be so much higher that will drive back the entire thing to positive value. TP is always positive, because otherwise it will create a non-causal system. That is not physical. It is how we define the delays. So that don't you don't have to remember that is just a fun fact. So now we need to define how this propagation delay, how can we measure this propagation delays, okay, from our knowledge of PMOS transistor, NMOS transistor, and how the circuits behave. So first thing is that, let's say you have an inverter. Okay, let me just first tell you about the switch model of transistors. So this is a NMOS, right? This is gate, this is drain, this is source. So when in on state, that means your VGS is greater than VTN. My NMOS behaves like a resistor, right? This is my on resistance. Do you agree?
Yes, sir.
And in off state, it should ideally behave like a
Open circuit.
open circuit. But that doesn't happen. We always get a off resistance. Why do we get off resistance? This is what we have discussed in our last class. That if you plot your VG and log ID, you will always see that this is off, means you are applying VG equal to 0. On means you are applying VG equal to VDD. So off means for an NMOS, you will always get a non-zero I off. And why do we get a non-zero I off, by the way? Last tutorial session I have discussed the reason. This is, by the way, called your
Subthreshold.
subthreshold leakage current. So as long as your temperature is not equal to 0 Kelvin, you will get a subthreshold slope minimum that is equal to your ln10 times kt. Okay, so you have a finite subthreshold slope. So in any, and your VFB for NMOS is generally negative. So you will always have a non-zero I off. Okay, and for that non-zero I off to flow into the from drain to source of the NMOS, you need to have a you will have a resistance. Okay, that is off resistance. But for the timing of the discussion and the simplicity of the discussion, we will ignore this part as of now. We will go back to this when we discuss our static power dissipation. So you understand that it is something like this. This is ideal. So how do you represent the switch model? It is something like this. This is your R on, this is your source, this is your drain, and this is your gate terminal. Okay. So when gate is on, current will flow from drain to source via a resistance R on. When when gate is off, the switch is open, no current is flown. So that is open circuit. Now let's say you have an inverter, okay, and a large amount of circuits are connected. I can represent this entire stuff as an inverter and a load capacitance. Why? The question is why?
So because all the circuits which were connected, we have made a equivalent capacitor and we have placed after the inverter.
Why it is a capacitance? Most of the things will be made of your MOSFETs only, right? So either you will be looking into this, your this terminal will be connected to this terminal or this terminal or this terminal. In anywhere you connect the MOSFET, mostly you will see a capacitance only. What do you see here? A gate capacitance, right? CG.
Yes, sir.
So mostly you will see the entire stuff like a capacitance only. Okay. Even the wires, these wires will be, by the way, what is the frequency of this signal? Let's say what is this is your time domain signal, let's say f of t. What is the frequency domain plot of this? Do you remember from your signal system course?
So I think triangular wave.
You have to just take Fourier transform, right?
Yes, sir.
It will be like sync pulses, right?
Oh, same place.
You remember, right?
Yes, sir.
So this thing has actually infinite frequencies possible because the sync pulses will die at your infinite range. Okay. So moral of the story is whenever a transient switching is happening, you understand that it is a very high frequency phenomena. And in very high frequency, how do your metal wires behave like? Transmission lines, right? Distributed elements. So there will be resistances, there will be capacitances.
Hmm.
So from that point of view, you will only see mostly the capacitances at the load input. So you can simply replace it with a CL. So that is the logic behind replacing the load with a CL or a load capacitance. So now if you draw your inverter, you have your VDD and you have your load capacitance here. Okay, this is how you generally represent. This is your V output, this is your V input. Fine.
Yes, sir.
Now when your V in is equal to 0, or let's say V in is transitioning from 0 to 1, what is happening basically? 0 to 1 means your 0 to 1, or let's say for the timing, let's say it is 0. So in 0, what is happening? What is your PMOS status and NMOS status? On or off? Please tell me.
PMOS will be on, NMOS will be off.
So in the on state, how did we model it? With a resistance, right? R on a transistor with a on resistance, right?
Hmm.
And NMOS in the off state, it is just an open circuit. And here we have connected an CL. This is VDD. So what will happen? This capacitance will get charged.
Charge up. Yes.
Similarly, let's say when your V in is equal to 1, what will happen?
PMOS will be off, NMOS will be on.
PMOS will be off, NMOS will be on. So that means this is your VDD, this is an open circuit, and here you will have a R on, and here you will have a
CL.
CL. So what will happen? The capacitor will get discharged, right?
Yes,
Whatever
sir.
will be stored into the capacitors, if it is 0, then doesn't matter. If it is some non-zero value, then capacitor will get discharged, right?
Yes,
So
sir.
you see there is a charging and discharging involved. And to understand that charging and discharging, what do we need to analyze? A first order series RC circuit. Both are first order series RC circuit. Can you see?
Hmm.
So now let's say this is C, this is R, and I have given a input signal like this. So what is the equation of V out? Can you quickly tell me? Let's say this is your 0 voltage, this is your VDD. You should be instantly able to tell, right? This is VDD times, these are basic stuffs. E to the power minus T over RC.
Yes, sir.
So what is happening? This is your input signal. So output will simply start charging with this rate. This is your V out and this is your V in, right? So how did we define our propagation delay? At that time it reaches the half point, right? Half VDD point. The time it reaches half VDD point. We had defined it like this, but in our case, we have taken our input signal with zero rise time and zero fall time. The example what we are taking, this one, right?
Hmm.
So to find out TP, what should we do? We just simply have to put this equal to VDD by 2 and replace T by TP. So what does it give? E to the power minus. So this cancel. TP by RC is equal to half. That means TP is equal to ln2 of times RC. That means your propagation delay is 0.69 times R times C. So this is very important, okay?
Yes,
How
sir.
we get this formula is very important to understand. So can you quickly tell me this is related to which TP, HL or LH?
So LH.
So TP LH will be 0.69 times
RC.
R
C.
on of P transistor times CL, right?
Yes, sir.
And what about this one? This will be TPHL, that will be 0.69 times R on of N transistor times CL.
Yes, sir.
Your discharging will be at the same rate, right? If you just do it, your capacitance discharges like this exponentially. And what is that equation? That equation is VDD times exponential minus T over RC. This is your discharge equation, capacitance discharge equation. You put here V out equals to VDD by 2, it will give you the same result. Okay. So charging and discharging are like this. So now what do you get? You get your TP LH is equal to 0.69 times R on of P times CL, and TP HL is 0.69 times R on of N times CL. So to have symmetric TP HL equal to TPLH, what should we have similar? We should have R on of P transistor should be equal to R on of N transistor.
Yes, sir.
So do you know how R on is computed? In an inverter dynamics, MOS transistor can be both in saturation as well as linear. This we have seen, right? While deriving the VTC, it can be in both of these. Cutoff we don't worry, because then my R on is simply infinity. It is an open circuit. So what is the equation for IDSAT and IDS lin? Half mu n Cox W over L VGS minus VTH whole square times 1 plus lambda VDS, right? This is the saturation case. And mu n Cox W by L VGS minus VTH times VDS minus VDS square by 2. This is my linear case.
Yes, sir.
So in linear region, we can ignore this term being small. So I can simply write mu n Cox W over L VGS minus VTH times VDS. Now what is your R on? R on saturation is what? 1 over DIDS sat divided by DVDS, because DIDS sat by DVDS will give you GDS, and 1 over GDS is your R on, right? So if you look at this will be proportional to what? Mu n Cox W over L and some
Sir,
constant other things. Yeah.
sir, how did you wrote 1 upon del ID side by del VDS?
What is GDS? Del IDS by del VDS
Yes, sir.
or G0? What is your R0 then? 1 over G0, right?
Yes. Okay, got it.
So if you take derivative of both of these, what you will find out that in both the cases, your R on is proportional to 1 over W by L times mu N or mu, let's say. And you know that in case of PMOS, in case of let's say CMOS, you take into account both of these. Your mu N is almost twice of mu P.
Mu P.
So that means you have to have your WP by LP twice of WN by LN. One problem we had solved in our last tutorial session. I told you that this will become helpful in the next session. So basically what you do to get similar iron, to get same iron or IDS, you just make your PMOS twice bigger. That means WP by L, or in other sense WP by WN, you make twice. That means if W by L is 1 in this case, it will be 2 in this case. So if you draw the layout, if this is your, let me just draw it in this way. If this is your W and this is your L for NMOS, your PMOS will be something like this, 2W and it will be L. Why? Because you want to have your area higher. Okay, by having your area higher, you can get your same R on, and that will lead to, this leads to R on P equal to R on N. That will lead to translate to TP LH is equal to TPHL. Okay, from this equation. So you see the logic behind making PMOS twice bigger than NMOS.
Yes, sir.
But what is the catch in that? By the way, do you want a higher propagation delay or lower propagation delay? Propagation delay, we want to minimize, right?
Hmm.
So TP is what? 0.69 times R equivalent, or let's say R on times CL. Okay. So how will you,
Yes.
so you have two controls, right? One is R on, one is CL. CL is not in your hand. CL is will be mostly determined by the load capacitance. That is the other circuit. So you can, how can you reduce R on?
Sir, by increasing the W by L ratio.
From this understanding, right?
Yes.
So R on can be reduced by increasing W by L. or L is generally your constant in the entire circuit. So you generally increase your W. But what is the catch with that? What about capacitances?
So they will also increase.
Why?
So because the width is increased, so the time to reach the charge from one position to other also increases. So the load increases.
Capacitance is equal to what? Capacitance is equal to epsilon A by D, right? So basically, this is your MOSFET. This is N plus. Let's say this is P. So you have a oxide here and you have a gate stack here. Fine. So what are the capacitances you have? This is your gate capacitance, mainly your oxide capacitance. You will
Yes.
have a capacitance in these regions, gate to source, gate to drain. They you will have a capacitance through, let's say you have a shallow trench isolation here. That is your SiO2, because your SiO2 will not be only on top of the gate. It will be out surrounding your devices also. So you will have your capacitances here also. But what is increasing basically when you are increasing your W, let's say earlier your device was till this much dimension. Okay.
Mm.
So this was your device dimension. Now what you are doing, you are increasing your W. So what was your L and W? This was your L and this was your W, right? Now what you are
Mm.
doing, you are increasing W. That means you are adding extra area, right? So now you have increased your W. So it is now 2W, let's say. So to reduce your R on, you have increased your W by L. So basically you
Yes.
have increased your W. So if you increased your W, what you are doing essentially to these capacitances, you are essentially increasing the parallel
Area of
plate area, right? This is your one plate, this is your another plate. So earlier it was till this much. So your capacitances were lower. Now you have increased this additional area, you have increased. So your capacitances will also start to increase. So this will also come into play in determining your delay. So CL is not actually entirely due to your load capacitance. And why am I saying that? Let's say you have an inverter. So you see you have a capacitance of this, or some capacitance. When you look into the gate, you will get a gate capacitance. Let's say this is CGP. You will also see a gate capacitance here. Let's say this is CGN. You will also see a source capacitance. Let's say this is your source capacitance, CSN. You will also see a drain capacitance, CDN, another source capacitance, another drain capacitance for this is drain, right? CDP, and you will also see another source capacitance, CSP. So these capacitances will also start to increase in addition to whatever you had your CL. So you see your delay is not only determined by your CL but also with this additional parasitic capacitances. So how do we simplify this? We ignored this because we have a direct path at this position. So we simply denote it one input capacitance, that is CGP plus CGN, and one output capacitance, that is CDP
CDN.
plus CDN. You see, right? It is parallel combination between these two ground terminal. So parallel combination of capacitances adds up, right?
Yes, sir.
And you have your CL.
CL.
So now, what is the delay of your single stage? Now, what is your TP? 0.69 times, let's say R equivalent, times your CL
CL.
plus,
CGP, CGN,
no,
CDP, CDN.
CGP is your this, right? Input side. Your charging path is, what is your charging path? Charging path will be this,
CD.
right?
Yes.
This will be simply this plus CDP plus
Plus CDN.
CDN. Okay?
Yes, sir.
And let's say CDN is equal to CD. So what will be my CDP? Can I write it 2CD?
Yes, sir.
Because my WP is twice of WN.
Hmm.
You see this, right?
Yes, sir.
So let's call this stuff as C internal. Why this is called C internal, by the way? This is the internal capacitance of the inverter which adds to the delay due to the loads capacitor also, in addition to the load capacitor. Ideally, there should not be any capacitances involved. But as we keep increasing our W, our intrinsic capacitances of the device, or these capacitances start to increase. So these also start to come into picture in determining your delay. So now we have our delay formula as 0.69 times R equivalent times CL plus C internal. Okay. The C internal is basically your drain capacitance. Now what we will do, to take into account this capacitances also, and why this is important, I'll just come back in a while. Let's call it C input. So what will I have? CL by C input plus C internal by C input. This I define as TP0, or the device's intrinsic delay,
Hmm.
and this I define as F, and this I define as gamma. Just for the nomenclature, remember it in this way. This is F and this is gamma. Okay, just two terms. So this will be my delay of the device. Now the question is, intrinsic delay of the device, is this TP0, is this width dependent? W dependency. So is TP0 width dependent?
No, sir.
Why?
So because there is no W term in the equation.
No, your R is proportional to 1 over W, right? R is proportional to 1 over W. Let us take L constant. So R is inversely proportional to 1 over W, or inversely proportional to W,
Yes, sir.
and C in is your gate capacitance. This is
Hmm.
proportional to W, obvious reason. This we have seen, right? Your area is increasing.
Yes, sir.
So this is proportional to W, and these two are multiplied. So
Okay.
W effect is not there, right? So TP0, W independent. Okay.
Yes, sir.
What about gamma? Gamma is what? Basically C internal by C
C.
right? C in is it your what? Gate capacitance basically,
Hmm.
and C internal is what basically?
Drain. Drain capacitance.
So here proportional to W, here proportional to W, this gets cancelled. So it is also independent of W.
Yes, sir.
What about F
So C in is proportional to W.
and CL
CL is
does not depend
independent
on
of
W,
W.
right? CL is independent of the device's dimension because
Yes,
CL
sir.
is outside entity. So your F is a parameter of W or transistor or let's say inverter size. Okay. So this is very important to understand. So how we will determine the sizing of the inverters? From the delay itself. We want to minimize the delay. Delay depends on R on and delay depends on your resistance and capacitances. We can see that we have manipulated the formula in such a way that resistance with dependency we have taken into account by nullifying it to some capacitance with dependency. So all dependencies are now coming back to how my CL upon C in ratio plays out. Okay.
Yes, sir.
So this is a mathematical manifestation for easiness of our future circuit analysis. Now we'll move on to the inverter chain analysis. So did I not did I miss anything? I think I was supposed to tell you guys something else also. This is our equivalent. This. Okay, just if I remember it, I'll tell you. So this is so far. Now what we'll do? Inverter chain sizing. Okay. So far it is clear, right? It is very important to understand this much. Then everything will become very easy.
Yes, sir. Clear.
Okay. Yeah. So yeah, now I remember. So what I was about to tell you that why this scene is important. Out of the blue, scene was not there in the equation. We just introduced scene, right? So you
Yes, sir.
must be thinking that why have we done that? There should be a reason. The reason being that let's say you have an inverter chain, okay? You have multiple inverters connected. So there will be a scene to this. Can you tell me what is the load for this? What is the load to this stage? The load to this stage is the input to this,
Yes, sir.
right?
Hmm.
So what is happening? This C in comes into picture when you have a multiple inverter chain. So stage 2's C in acts as load of stage 1. Is that statement clear?
Yes, sir.
Okay. So if that is clear, so now let's see. Let's say this is my TP1 delay, this is TP2 delay, and this is TP3 delay. Okay. So what is the total delay?
TP1 plus TP2 plus TP3.
How can we do that?
Sir, we will add the individual delay of every
Means why do you do that?
sir, because see internal every
No,
time it is changing.
there is basically something called critical path. Okay, so if you have multiple paths, no, you only add the delay of your critical path from input to output, which contributes to your maximum difference or maximum delay. That is contributed by adding individual elements. If you work in any project management companies, you see for a project there are multiple sub works. Okay, so the longest path to start a project and to finish a project, the longest path it takes is called a critical path. Similarly, in case of circuits also, you may have multiple branches. You may have another branches here, but if this path takes the longest delay, this is called the critical path. But in our case, we have only in inverter chain one path. So we'll keep on adding the individual delay of the transistors, or individual delay of the inverters. Okay. So
Yes,
now
sir.
tell me, so this is the formula wise, this is this plus gamma 0 plus F0, sorry, gamma 1 plus F1. From this formula, I am just writing this down. Similarly, this is TP2 times gamma 2 plus F2 plus TP3 times gamma 3 plus F3. So as we are trying to do the transistor sizing. So this is size independent, gamma is size independent. So what we will have? We will have TP0 times 3. In our case, we have taken the example of 3 stages times gamma, let's say, and then plus I will have TP0 times F1 plus F2 plus F3. This will be my total delay.
Yes,
Now
sir.
I need to minimize this, right? Our end goal is to is the delay minimization. So now if I write it in general form, so this will be TP0 3. Let's say I have n stage, so n times gamma. Then I will have TP0 times F1, F2, let's say Fn. Okay, I need to minimize this with respect to something. I need to minimize this with respect to something, that is the sizing. So by the way, what is my F1? F1 will be
CL by C internal.
C.
CL internal by CL.
C. What is F1? F1 is your load by C in, right?
Yes, sir. CL by C internal.
So what is C load of first stage? Is C in 2.
CL one.
Do you see this? Is this okay?
Yes, sir.
Then this will be C
Yes,
in
sir.
3 by C in 2. Similarly, let's say I have a intermediate stage where C in J by C in J minus 1 plus C in J plus 1 by C in Jth stage, then so on till nth stage. I need to minimize this with respect to C in J. So C in J comes into only two terms. Fine. It
Hmm.
comes to only two terms. So this will be equal to what? This is 0 independent of C in J. So this is 0 independent of C in J, independent of C in J, and everything will be independent of C in J. So now this becomes If we derive with this, differentiate with this will become C in J minus 1 plus this will be C in J plus 1 minus 1 over C in J
C in
square,
J square.
right? So
Mm.
when you minimize, this will become 0.
Yes, sir.
Maxima or minima at that slope is 0, right?
Yes, sir.
So if you solve this, you will get C in J plus 1 by C in J is equal to C in J by C in J minus 1. That means what? That means your F of J minus 1 is equal to F of J. That means what? It is in generic form. In our case, this translates to what? This F1, F2, F3 should be equal.
Yes, sir.
That means F1 should be equal to F2 should be equal to Fn.
F3, F1.
Our case, F1 should be equal to F2 should be equal to F3, right?
Yes, sir.
Now in the question, what is given? Let's copy this image. So this is given as, so your CL by C1 is given as 27, right? So CL by C1 is what? CL by C1 is equal to CL by, let's say this is C3, let's say this is C2, and this is C1. So CL by C1 is given. So CL by C1 can be written as CL by C3, C3 by C2, C2 by C1, right?
Yes,
So
sir.
this is nothing but your F1 times F2 times F3. So this is F cube, because both all of these are same. This equal to 27. That means your F equals to 3. So what does that mean? That CL and the ratio of CL by C3 is equal to 3. C3 by C2 is equal to 3. C2 by C1 is equal to 3. So from this, can we get the understanding of the sizing of the transistors? Yes, we can, because what are these C's? These C's are basically your gate capacitances, right?
Yes, sir.
Why do you know that it is gate capacitances? Because these are all C-ins, right? These C-ins are this C-ins proportional to W. This C-in is gate capacitance, right?
Yes, sir.
So that means what? If the size of this transistor is W by is the size of this transistor is W by L, so C2 will be thrice of that. That means the size this will be 3W by L, and this A3 size will be 3 times of that. This will be 9W by L, right?
Yes, sir.
So your correct answer would be A2 is 3 times of A1, A3 is 9 times of A1. Similarly, in the next question, it is asked that calculate the delay. Consider self-loading factor is this. So delay, what we got? Delay we got as TP0 times 3 times gamma plus TP0 times F1 plus
F1.
F2 plus F3. So this is your TP0 times 3 times 1. Gamma is given as 1. And this is TP0. And what was my F? F was
3.
3, right?
Yes, sir.
So total I will get 12 TP0. So did you understand how the delay thing has come? It has come basically from simply the RC circuit. So what are the things you need to remember in this case? You need to remember this formula. This is very important. You need to understand where this is coming from. Okay, this is coming from first order RC circuit. Then you need to understand what? You need to understand how you are making your TPHL and TPLH same. This is another key point. Then next point is you need to understand this equation capacitance. So your capacitance will, the internal capacitance will start to add on to the load capacitance. So this will come into parallel of CL. So all your charging and discharging will be this entire thing, right? Parallel combination of this thing, because this also you need to start to charge. Then next is, this is your simple formula. So, and then to accommodate the inverter chain problem, we have introduced and we have taken C in common and divided it into the bracket to get two quantities F and gamma. Okay, this F is nothing but the ratio of your load capacitance versus the input capacitance of the first stage, and this C internal by C in is your self loading. That means how much your drain capacitance with respect to your gate capacitance. Okay, so then
Yes.
everything is just simple. This you understand from this part to arrive at this part, it is very simple. So what I want to emphasize that do not remember the formulas. Okay, it will not help you. It is better to understand the things so you can just quickly do it. You practice 3 4 problems in this similar line, you can just then easily, just looking at the circuit, you will be able to tell. Okay,
Yes, sir.
so moving on to the next problem. Yeah, now so far what we have discussed, you should be able to answer this. In a CMOS inverter, increasing the PMOS width, what is my TPLH and what is my TPHL? This is 0.69 times.
R on
TPLH means what? Low to high, output is low to high, that means output capacitance is charging. How will output capacitance charge? When it is connected to VDD, right? Through which it is connected to VDD, it is connected to PMOS. So it
PMOS.
will be R1 of P times some load capacitance. And high to low is the discharge path. That means NMOS. N times CL plus CD. CDP plus CDN. CL plus CDP plus CDN. So from these two equation, tell me WP if you increase, so your R on P will increase, right? And what will increase? Your CDP will increase. Sorry,
So
your
R
R
should
on
be
P will
decreased.
decrease and CDP will increase.
Yes, sir.
So improves means, what do you mean by improve? You want to decrease or increase the delays?
Decrease.
Decrease, right? So from these two equation, can you tell me what is the answer?
Sir, it will improve TPLH.
It will improve TPLH. Okay, and let's say TPLH. And what is the second part?
It will degrade TPHL.
Why? What are the culprits here? These two are the culprits here, and this one is the culprit here, right?
Yes, sir.
It seems to be obvious that this will degrade,
Yes, sir, because CDP is increasing.
right? But it is not obvious, right? What you have told. It is not that much obvious. So why did you tell this? Because this is increasing, this is decreasing.
Okay. So that R on is decreasing much at a faster rate.
No, both are proportional. See, this is proportional to 1 over W. This is proportional to W. So, what you need to understand to solve means, see, you have answered me the right answer only, okay? But you need to understand this, right? Why this is happening. So, what is your TPLH? 0.69 times R on P times CL plus 0.69 times R on P times CDP, let's say CL plus CDN, okay? CL plus CDN plus 0.69 times R on times CDP, okay?
Yes, sir.
This part remains constant with W, right?
Yes, sir.
And this part decreases with W.
Yes, sir.
So TPLH is decreasing or increasing?
So decreasing.
Decreasing, right? So you should have
Yes.
told me in this fashion that it is a sum of these three. One part is constant. Yes, I agree that this is decreasing, this is increasing, this is constant. So let us take it out. So the remaining part, what will we have? We have a product term where this is independent of W, WP. This will be dependent on WN, but not WP, right?
Yes, sir.
So R1 will be decreasing. So overall TPLH will be decreasing. So this answer is right. You understood, right?
Yes, sir. Got it.
Okay. So for a combinational logic gate, alpha is equal to 2. This is this. Calculate the power dissipation. So power dissipation. Okay. So you have two types of power dissipation mainly, right? Your static power dissipation and your dynamic power dissipation. So first tell me what is static power dissipation and why does this happen? Basically, what do you mean by power dissipation? You have some VDD connected to some circuit, right? And this is ground. So if you have a path from this to this and current is flowing, that means what? This VDD or the power is wasted, wasted or used from the supply. So this is what we call as your power dissipation by the power supply. Okay. So in case of your static power supply, static means when there is no change of state. When there is no change of state, that means your circuit is sitting idle. That means for, let's say, this is your inverter at input, you have applied this pulse. So at output you will get what? You will get this kind of thing. So this region is called your static or steady state region. During this region, during this time, what is the power that is being wasted or dissipated? That is your static power dissipation. So let's say this is your 1, right? This is 1. That means your transistor NMOS is 1 and PMOS is off. So what will happen basically? There is a off resistance connected here and there is an on resistance connected here. Okay. So what will happen is that if you consider your PMOS or VSG at 0 case, you will have a certain I off, right? This is called your leakage power. So this leakage power will be there, and on top of that, you will have your diodes connected, right? So this is your drain. So drain will be your N type. So basically what is happening, these diodes will also start to leakage. What are these diodes? These diodes are this N plus and P. So this is the diodes that will also, these drain body diodes will also contribute to your leakage power. So static power dissipation is basically your leakage power dissipation. Okay. It is defined as P stat equal to VDD time I stat. And this I stat is basically your leakage current. Ideally, static power dissipation should be 0. But short channel devices, for that matter any devices, this started to increase. And this is causing so many issues in the devices nowadays. For example, if you charge your mobile phone and just do not do anything, after a few hours or like couple of days, it will get discharged. So where is that power going? This power is flowing in the idle state. That is the static power dissipation. Okay. So
Yes,
this
sir.
static power dissipation also creates heating issues in the devices also. But this static power is comparatively much more lower than what we will discuss now, the dynamic power dissipation. So what does this dynamic power mean? Dynamic power means, suppose you have this R on, right? This R on P and this is VDD and this is CL. So you need to charge this capacitance. So what will be the power supplied by VDD or the supply rail? Any capacitance you need to
VDD.
charge? What is that?
So VDD into ID.
No, no, VDD into ID, but capacitor is charging, right? ID is not constant.
Yes, sir.
So this will be CL times VDD square, right?
Hmm.
How do you find that out?
So it will be half CL VDD square.
Okay, let us see. This PT, we are talking about what power the sources has supplied. Okay, so we'll
Okay.
source voltage and we'll multiply it with the current. By the way, this is your energy, okay, not power. So PT will be VDD times IT. IT is this current what is flowing.
Hmm.
So what is your IT? IT is your CL D V out. Let's say this is V out, VO of T, dVo of T by dt. So your PT times dt, VDD, CL, dVot. Then you will just integrate it. T will integrate from 0 to infinity, and this output will be 0 to VDD. Why I am taking 0 to infinity? Because ideally the capacitor should take infinite amount of charge to reach this point, right?
Hmm.
This reaches VDD at t equal to infinity, okay? So this we call it energy supplied by source, E source is equal to what? This derivative, this integration is CL VDD square.
Yes, sir.
What you have told me is the how much power is stored in the capacitor. So how do we find that? PC of t is what? V0 of t times I of t.
Yes, sir.
So what is that? PC of t, V0 of t, CL dV0 of t
By
by
DT.
dt. Now if you integrate in the same fashion, PC of t dt, CL V0 of t times dV0 of t by dt, 0 to VDD. So you can see that energy stored in the capacitor is half CL VDD square.
Yes, sir.
So what will be, why does the half of the other power goes? This is supplied by the power supply, right? In the
Yes,
same
sir.
time duration. This is the supplied energy and this is the stored energy. Where should the have other energy go?
So it will go out from the capacitor, and in this case, it will flow to the ground terminal.
No, it just gets dissipated as heat through this resistor. The current is flowing across this resistor also, right? Let's say PR of T. What is PR of T? IT. And what should I take for VT? What is the voltage across the resistor? Can you quickly tell? It is VDD minus V0 of T. Voltage across the resistor, right?
Yes, sir.
VDD minus V0 of T. So in the same fashion, PR of T, CL dV0 of dt, VDD minus V0 of T. So if we integrate 0 to infinity PRT dt. And what is the voltage I should take of V0? V0 is 0 to VDD.
Hmm.
CL dV0t times your VDD minus V0 of t. If you do the integration, you will find that energy R is equal to half CL VDD square. Okay. So this half energy is dissipated through the resistor as in terms of heat. Got it?
Yes, sir.
So now tell me what will happen in the discharge case. This is your R on N and this is your CL. So this will discharge through this path. So the stored energy, this EC, will get discharged via ER, right? The stored
Yes, sir.
energy was EC. It will get discharged via R on and in terms of heat, obviously.
Hmm.
But in this case, do power supply do supply rail provide any energy?
No, sir.
It is not providing any energy, right? The battery is not providing any energy. So how do you define your P dynamic or power dynamic, power dissipation dynamic? Is your half times CL times VDD square times how frequent your output is changing from 0 to 1,
Hmm.
because only in 0 to 1 your power supply, sorry, this will not be half here because this is what we are talking about, supplied power. So supplied power will be C VDD square times the frequency of 0 to 1 transition at the output.
Yes, sir.
Fine. So if this much is fine, this is okay for an inverter. But what about a large circuit? Large combinational circuit. By the way, I hope you understand what is combinational and sequential mean. You guys know, right? What is combinational and sequential?
Yes, sir.
If you have only logic, this is your input. This line, the dashed line symbols, multiple input. Okay. This out. This is your,
Combinational.
and if you have logic, but in loop, if you have memory or state and input and output, so this is called sequential. Means it can store some previous state, output states also, and take this at input, take that as input and use it to compute again. Okay. So coming back to the point, for a combinational logic, your P dynamic is defined as CL VDD square times f of 0 1. It is changed to P of 0 1 times f of clock. This is applicable for synchronous circuits. Okay, synchronous circuit means suppose you have multiple paths, you want that at this instant my operation should start. Okay, to synchronize that you need to have some clock input signal, and clock frequency is the highest possible frequency you can have on a chip. Okay, so can you tell me what are the typical clock frequency you have heard of? Microprocessor clock frequency.
Sir,
Today's state of the art is 5 gigahertz. Okay, it is not increasing. Why it is not increasing? As you can see that if this increases, your power P dynamic also increases. So your device tend to heat up much more. Okay, because half of the power is dissipated as heat.
hmm,
So in today's technology, how then if your clock is not speeding up, then how do you have faster and faster operations? You do it by having multiple cores, right? You have heard of 8 core processor, 16 core processor, 64 core processor, right?
yes,
So you divide your job into multiple, assign it to multiple cores and do some kind of parallel processing. So that is, suppose I have 64 core, that is equivalent to increasing my clock frequency by 64 times.
hmm,
Okay. So this clock frequency determines what should be your maximum speed of the switching or 0 to 1 transitions. That is what digital circuits and microprocessor does actually. Then what is this P0 to 1? It is called alpha or activity factor. This is the probability of 0 to 1 transitions at the output due to a clock signal. For example, suppose you have a clock signal will be something like this. Okay, let's say this is your clock, and you are having your 0 to 1 transition only at this place. In other places, it is just idle. So your power is getting dissipated only in this region, right? It is not dissipated over the entire clock frequency range. So how do you deal with that? You define an activity factor. This activity factor tells you probability of 0 to 1 transitions at output due to clock signal presence. Okay. So your final P dynamic becomes what? CL VDD square F clock times alpha. Okay. Now this is what? This is how much power that has been supplied by the source. So if someone asks you to, this is supplied. If someone asks you to determine the dissipated power, means P dynamic dissipated. So what you will do? You will just multiply it with half. Okay. So CL VDD square F clock times alpha. Now in our question, it was asked that circuit power dissipation is needed to be found out. So P1, let's say your 150 times 10 to the power minus 15 CL, that is your CL. VDD square is your 4. F clock is your 2 into 10 raised to 9. And alpha is your zero point 0.2, right?
yes,
And you will have a half factor in front. So if you compute, this will be minus 6 and this will be 120. So 120 microwatt. Okay. Similarly, your P2, calculate circuit power dissipation and VDD equals to 1.5. So obviously you can directly find it out, 1 microwatt divided by this 4. times 1.5 square.
1.215 square.
That is 2.25, right? So if you
Yes.
compute, it will be your 67.5 microwatt. So this will be your right answer. So you see, understanding. So this part, I think, is the detailed understanding which you require, that what is the supplied power, what is being stored into the capacitor, load capacitor, and what is being dissipated through the resistor. Everything you can calculate using the simple definition of this. And also note that these are energies. And what is the unit of energy? Joules, right? What is the unit of power? Joules per
Watt.
second or watt. Joules per second is watt actually. So by per second is captured in this frequency term. Okay. So
Yes, sir.
that is how you are converting your energy to power. So I think we are well above time today. So see you on Friday. So by the way, next lecture will not be on Sunday. Next week's lecture will be on Friday 6 to 8. Okay.
Okay, sir.
Okay. Thank you. Let's end the session.